All right, welcome back to the Kitchen Research Group. We have a new publication out recently that was a collaboration with an undergraduate at Carnegie Mellon University named Aaron Garrison, who did almost all of the work in it. Postdoc Javier and professors Gabe Gomez and Zach Ulisse, and our colleague Samuel Blau, who worked on applying large graph neural networks to predict transition metal complex energies using a modified data set that I'll tell you about in a little bit. This just came out in the Journal of Chemical Informatics and Modeling, and you can find the DOI here or in the video description. So in a nutshell, we took an existing database, the TMQM database, and ran it at a higher level of theory to get a more consistent data set and removed a few problem structures from it. And then we trained several graph neural networks to make predictions on energy of these species. So these transition metal complexes are molecules that have transition metals in them. They're very common in homogeneous catalysis and inorganic chemistry. And the thing we were interested in this work is whether we could use graph neural networks to predict energies of these molecules. That's a first step in being able to predict other properties like reactivities or reactions or reaction barriers, etc. What we found is the data quality is super important. So with the original data set, there were some non-systematic errors that we found, and those went away when we removed some unrealistic geometries that were, say, missing some hydrogens and missing some other things that made them unrealistically high in energy and hard to fit. And we also recomputed the data set at a higher level of theory, and I'll show you where that impacted the data. But after we did that, we got quite promising results in fitting these graph neural networks to the data set, and we got a much more consistent distribution of errors across it. And finally, we took a pre-trained model from the OC20 Open Catalyst project, and that led to significant improvements in the predictions, indicating that we can use these pre-trained models and that there is transferable knowledge that leads to better ML models even in molecular and homogeneous systems. Okay, the data set was about 86,000 structures. These were originally computed at a lower level. We recomputed them at this higher level of theory. And again, we removed a few problematic structures that were missing hydrogens. We ran all of those through a workflow that's described down here using PyMatGen, Custodian, Fireworks, Atomate, and so forth. And that's how we were able to get the large data set computed. We had 4 different graph neural network models, SCHNET, SpinConf, Pain, and GemNet-T. These are kind of roughly an order of complexity and order of size of models, and we used several different train val test splits of that 86,000 data set to look at learning curves, so we could go from 80 to 20% on the train, and different levels of test and split for testing and validation. All right, so here's the results with the original TMQM data set. You can see on these parity plots, we saw these large groups of outliers that we could not get to go away with any model. So it wasn't really a problem with the model complexity, but very much appeared to be an issue of the data. And when we ran the TMQM with this higher level of theory and retrained on this, we saw a lot of the issues were mitigated. And so you still see a few things that are outliers here, but for the most part you see a lot of the big stuff here has gone away. All right, the error distributions also depended on the data set. So here we show something like t-SNE or UMAP dimension reduction. So you can see there's a lot of clustering on all the different kinds of metal complexes. So we have the ruthenium, iron here. And when we look at the TMQM data set, you can see that a lot of the errors that I showed you were concentrated in these 2 specific cases. So something was not right with the iron and ruthenium, or something was not consistent with these across the rest of the data set. And then after we reran all the calculations at a higher theory level, you can see down here the errors are much more systematically and uniformly distributed. We don't really see this kind of concentration, again suggesting that at the higher level of theory we get a better level of consistency across the data set. The very best model that we got of all is when we took the OCP model that had been pre-trained on millions of heterogeneous slab calculations and used that as an initial guess, if you like, for pre-training or fine-tuning on this. And we got quite a lot of improvement in the performance of the model by doing that. All right, so in summary, we have shown that the graph neural nets, all of them show significant potential for MLPs for transition metal complexes. We have found issues in data quality being important. If we have unrealistic high energy structures, that adds a nonlinearity that's hard to fit. And if we have inconsistent data across different subclasses of the data, that shows up like errors or noise. And by eliminating those, we got a much better model. We showed that fine-tuning a pre-trained model is better than training these models from scratch. We got lower errors and overall better fits. There are a few open challenges left. We still don't have a good way to include open shell complexes and reactive intermediates in this data set. So at the moment, it's still not totally suitable for calculating reaction mechanisms and reaction barriers and energies. And these models don't account for different charge and spin states. So if those are features of these mechanisms, then our models are not able to get there yet. Nevertheless, it looks very promising, and as models get better to be able to account for these things, this is a promising approach to being able to screen and explore transition metal complex spaces. The paper is open source. You can find the DOI in the video description, and you can read all about the details in the paper. Thanks for listening, and see you next time.